Hello everyone, I am Lars, part of the PlanOpSim team. PlanOpSim is specialized in simulating meta-services and offers an easy-to-use graphical user interface available online. However, some applications demand an efficient way to iterate over different designs. To this end, PlanOpSim offers an SDK which allows you to make a simple script that enables this and allows you to save the results directly onto your computer. To demonstrate the SDK capabilities, we have picked the well-known bezel beam as an example. In refractive optics, the bezel beam is generated by an hexagon and is characterized by its cone angle. A lot of interesting properties of the bezel beam change with changing cone angles. For every cone angle, the lens has to be redesigned. To do this manually would be cumbersome, so this demonstrates the SDK can be of great use. To use the SDK, a Python script is needed. I will spare you most of the details, since most of them are about connecting to the PlanOpSim servers. This is exactly what this first block of code does. After you're connected to the PlanOpSim servers, a wavelength and diameter of the component have to be specified, which is done here. So after this has been specified, a new component has to be created. I've named the new component bezel beam wavefront loop, and I've created them in this line of code. So this new component needs two main things, mainly a set of structures for which it can optimize the design, and it needs a target. The set of structures are called the NIST pillars in this case and are loaded in this line of code. The near-field wavefront target consists of two things, mainly a phase and an amplitude. In this function, the near-field wavefront target is returned in the form of a string, and the phase is specified here, and amplitude is specified here. So now that the near-field wavefront targets and the structures are loaded into the component, the design can start. Before designing, we want to specify for which different angles of incidence of the bezel beam we want to design, and we will loop over all the different angles of incidence. This is done in this code, in this line of code here. So in the loop, you can see that a new component is designed for every angle, and that this component is analyzed for every angle. The far-field wavefront in this example is analyzed, and the accuracy can be specified in the rows count and in the columns count parameters in this function. After the design and analysis are done, the results are saved in a form of JSON files, which you can name however you want, and will be stored directly onto your computer. Now that the results are saved in a form of JSON files on your computer, you can post-process this data and get some actual plots. So after all the heavy analysis and heavy simulation work, we can finally look at some results. On the x-axis you see the angle of incidence, and on the y-axis you see the width. The gray dashed line represents a theoretical predicted results, and the crosses represent simulated results. And as you can see, the simulation follows the theoretical predicted results very well. Also, the gray dashed line stops at a certain angle and a certain width, meaning that refractive optics cannot go smaller than this particular width, while meta-surfaces can go smaller. This means that meta-surfaces outperforms in this aspect refractive optics. Also, for every different angle of incidence, a new component had to be designed, so this also showcases the use of the SDK. If you're wondering about why artificial cells were used to correctly produce the results of the higher angles, you can always send an email to jonas@planopsim.com. Thank you for listening.